Today I'll be talking about context-aware transformer transducer for street recognition. End-to-end speech recognition has difficulty recognizing rare words. One approach is to use the personalized contextual information at inference time to boost the rare words. For example, shallow vision. The approach happens at inference time, so it's post-training integration. It, however, requires the external language models to rescore ASR outputs, and is sensitive to rescoring weights. In this work, context biasing networks are proposed to take advantage of the contextual information. A transformer-based ASR system is jointly trained with the proposed context biasing networks. To encode the contextual information, the authors investigate a bidirectional LSTM and retrain BERT. The bidirectional LSTM context encoder is trained from scratch. Note that we can use an existing transformer-based ASR system and freeze this during training context biasing networks. It's because training transformer-based ASR system from scratch can be expensive. This work showed that CAT, or context-aware transformer transducer, using BERT-based encoder, obtained 24.2% with error rate reduction over a baseline non-contextual system. There are two main kinds of methods to integrate contextual information in end-to-end ASR system. Post-training integration, such as shallow fusion or diffusion, and during training integration approach. The most relevant to this work are contextual, last, listen, attend, and speech, as proposed by Google. The CLAST used additional context encoder with location-aware attention. Another work is contextual RNNT. It applies simultaneous mechanism, but using the RNNT. Moreover, phonetic information will also investigate to further improve CLAS. In this section, I present the proposed method, which is the context-aware transformer transducer. An end-to-end ASR system receives a sequence of audio frames X and outputs a probability distribution over a sequence of token Y, for example, subword tokens. A transducer-based ASR system has three main components: an audio encoder, a label encoder, and a joint network. An audio encoder receives a window of audio frames centered at frame T and outputs audio embeddings. Label encoders use previous non-blind tokens to produce label embeddings. And lastly, the joint network combines the audio embeddings and label embeddings to produce the new embeddings. These new embeddings are used to predict the most likely token for frame speech T. In transformer transducer-based ASR system, audio encoder and label encoder are stacked transformer networks. The question is, how do we incorporate the context encoder in the framework of transducer? In context-aware transformer transducer CAT, two additional components are proposed to use the contextual information, the context encoder, and the biasing layer. Context encoder encodes a list of contextual phrases, while biasing layers combine the contextual embedding with either audio embeddings, as shown in left figure, or both audio and label embeddings, as in the right figure. Context encoder encodes a contextual or personalized entities such as contact names or device names. The hypothesis is that target entities exist in the K entities. During training, we can ensure this because we know the target transcription. But during testing, we don't have target transcription as well as a target entity. As the result, we sample K personalized entities of A speakers from their personal data. The authors explore bidirectional LSTM and retrained BERT models as context encoder. The BLSTM-based encoder is trained from scratch. With the ASR system, unlike previous works, a retrained BERT model was also investigated. The BERT model was retrained with a substantial amount of text data, while the BESTM encoder will return on the pair of text and audio. The second component is biasing layer. It used a multi-head attention to combine contextual embeddings and audio label embeddings. The query is calculated from either audio or label embedding. The key and values are calculated from context embeddings. The idea is we let the ASR system learn to pay more attention for audio frames corresponding to contextual or personalized entities. In this section, we present the experimental setup of this work. a 1,300 hours of speech utterances are divided into training, test, and depth sets. The speech data contains personalized device name, entity names, device settings, and device location. The table shows examples of this entity. For example, Roku Second TV as a device name. We define the relevant context as the entities in transcription and otherwise as less relevant context. During training, context encoder receives 100 contextual entities for each batch. We use 100 relevant context if possible. Otherwise, keep adding less relevant context until reaching 100. As a result, each utterance is paired with variety of context. This sample technique allows flexible during inference because model does not make assumption about what contextual phrases will be used. Assume the contextual phrases are always present during inference. For evaluation, depth and test sets are further divided into two categories, personalized and commons. This table shows examples sentences in the two categories. For personalized test set, we have turn off Ben's second TV. While for common test set, we can have dim living room light 30%. This section presents comprehensive experiments to evaluate the performance of CAT. In the first evaluation, CAT works compared to a non-constant contextual baseline and shallow fusion. TT denotes non-contextual baseline transformer transducer. SF denotes shallow fusion, and C denotes context encoder. These tables show word error rate reduction over baseline non-contextual transformer transducer. From top to bottom, we have transformer transducers baseline TT, the baseline with shallow fusion, the CAT using BLSTM based context embedding, the CAT using BLSTM based context embedding and shallow fusion, the CAT using BERT contextual embedding, and the CAT using BERT contextual and context embedding and shallow fusion. The CAT outperforms the baseline transformer transducer in terms of word error rate reduction. And leveraging the small BERT helps CAT achieve the best word error rate reduction. And lastly, combining shallow fusion and CAT further improves the performance by 6.3% relative word error rate reduction for personalized test set and 6.5% for common tests. Note that small BERT encoder has 14 million parameters, which is similar to baseline transformer transducer. To fully take advantage of the strong semantic prior knowledge of birth, a larger transformer transducer baseline was explored. This table shows with a rate reduction for a 22 million parameters transformer transducer baseline. The performance was further improved by 15.3% for personalized dataset and 13.4% for common dataset. In this second evaluation, different queries are explored to obtain contextual information. Specifically, audio query is compared to audio and label query. This table shows whether read for baseline transformer transducer, cat using audio query, and cat using both audio and label query. Using both audio and label queries achieved best result 10.9% for personalized dataset and 9.7% for common dataset. In the third evaluation, the author investigated the impact of the number of contextual entity K. The figure shows the word error rate reduction on the y-axis over transducer transformer. The x-axis shows the number of contextual entities, or K. And we can see that the word error rate reduction remains across different datasets with different value of K, the red and black lines. In the last evaluation, cat was compared to contextual LATs. The table showed the word error rate reduction over CLATs for 14 million parameters baseline transformer transducer. With the same kinds of contextual embedding, bidirectional LSTM, cat achieves 4.6% word error rate reduction over CLAS for personalized dataset and 3.2% for common dataset. The pre-trained small bird contextual embedding further improved the performance on both datasets, 13.6% for personalized and 10.6% for common. Using larger transformer transducer baseline further improves the performance. 19.4% for personalized dataset and 14.8% for common. In conclusion, this work proposed CAT to enable transformer transducer to use contextual information, leveraging both BLSTM and pre-trained BERT to encode contextual information. We could get significant word error rate reduction. The relevance of context is measured by cross-attention mechanism with audio embedding alone or both audio and label embedding. CAT outperforms non-contextual model, shallow fusion, and CLAST on an in-house dataset with personalized entity.